Hi, thanks everyone. So just maybe, as kind of already said, my name is Liam Kirwin. So I'm currently at QB. It's a large insurance company. We do corporate insurance, so B2B, and the data science team does a lot of different things. The two big categories of those are risk models and fraud models. So that can be things from motor fleets to professional indemnity for lawyers to wind farms, international shipping. So lots of different things to figure out how risky they are. And lots of the data is categorical, and lots of it is pretty messy, is long. Data sets that 20 years ago were just a set of Excel files, and sometimes today are still like, until quite recently, we're on Excel. So there's lots of experience doing this kind of thing. And the talk, yes, in case it wasn't totally clear, CAT is short for categorical variables. So just anything that's not a number. Often in Python and programming languages, these are some string, basically, that you have in your data. There are a lot of different strategies for dealing with them. So today is kind of an intro-ish level talk about different strategies for dealing with them. So I'm going to assume basic familiarity with Python and scikit-learn and things like that, but not too much else. The context I'm going to be talking about is kind of standard supervised learning. So just not talking about unsupervised learning and not at all about neural networks and other things. It's kind of too broad a topic otherwise. And there will be what I hope is a tasteful number of cat kits. I was just struggling over what the right balance was, but we'll see how we go. So there's basically three sections. First, let's talk about different encoding strategies, what they are, pros and cons. Two, a few things to think about general strategy, like when you have categorical variables in your data, what should you think about doing, in what order, how should you approach it? And three, I'm going to talk specifically about three packages. So XGBoost, LightGBM, and CatBoost are kind of far and away the most popular gradient boosted decision tree packages and are super common, real world, CAGL everywhere, and they deal with categorical variables very different ways. In some ways, that's one of the key differences between them, so it would be interesting to dive into that just a little bit more. Yes, all right, so just quick definition before we start. To maybe what you call it, families of categorical data. So you can have ordered data, where there's some kind of low to high thing. So, or maybe this one, agree, neutral, disagree is high to low. There can be a bit of variation within here. There can be stuff that is, maybe the levels are quite even. Maybe this you could think of representing it as 1, 0, -1, and that would be pretty fair. Other times you can have ordered categories where the gaps between them might be quite big, so it might not be totally fair to just assume some numbers. And probably the more common, almost certainly the more common kind of categorical variables is unordered. You have a bunch of categories in no particular obvious order. Okay, so section 1, cat encodings. Cat coding. All right, so first off, I have the two standard scikit-learn things. So label encoding, it's also called ordinal encoding, various other things. I think one thing about this area that's tough is there's a lot of different names for the same kind of idea. But this is basically where you would just assign each level of the category an integer and do nothing else. So it's really simple. It's kind of just a one-to-one mapping. The major big problem is this might imply an ordered relationship depending on the modeling context, and that's if the variable is ordered, maybe that's okay. If it's unordered, then it's like almost certainly not a good thing to do. So the simplest thing to do, but not, I think, very uncommonly the right thing to do. One-hot encoding is perhaps like the classic default thing to do with categorical variables. So same list of categories. We'll transform into something that has 3 columns, 1 row for each observation, and we have 1 column for fuzzy, 1 for smooth, 1 for soft, and if it's 1, if it's the observation has that category, and it's 0 if it's not. And so this is a one-hot encoder in scikit-learn. It's perhaps like the standard thing to do for many algorithms, and the right thing to do for many algorithms. But the main downsides, there's a bit of a two in one, 2 sides of the same coin kind of thing. If you have a lot of levels, which is quite common in real world data, you'll end up with a huge number of columns in your resulting matrix. You can imagine like 10,000, 100,000, depending on your data set. And this is going to have 2 impacts. Similar, different. One is, it's just going to use up a lot of memory. And so if your data isn't trivially small, you might run into performance impacts. Maybe you need to find a bigger machine, or it just takes forever to fit your models. Also, for a lot of algorithms, this is going to start impacting the quality of the solution that the algorithm can find. It's just kind of too many choices to cope with well. I'll talk about that a little bit more later. So that's, strategy 2. Count encoding. This is like I think in my mind, like slightly more reasonable version of label encoding. You still get a nice kind of one-to-one mapping. Like the output is the same size as the input, so you don't have the explosion you'll get with one-hot. But instead of replacing it, just assigning a string to an integer, you replace it with the count of the number of times this level showed up in the training data. So here we have fuzzy and soft each show up once, smooth shows up twice, so it gets 2. And I think so it's kind of similar to label encoding. It's, I think, a little bit better in general because it's plausibly useful. Separating, arranging them in order of small to big on a number line is probably more useful than a random ordering. And you can think of an algorithm like a tree-based model easily using that to create another category. Like anything below 10 examples is just grouped together in the same leaf and treated together. So if, for various constraints in a real world problem, if I had to do something like label encoding, I would probably do that instead. And there's a history of this being used quite successfully on Kaggle, I think, which is one of the reasons I want to throw it in is doing like count encoding into XGBoost or something was a very quite a popular strategy for a while before some of the newer packages came out. Okay, so next is target encoding. It's kind of the most basic version of target encoding. Just replace each group with the mean of the target variable within that group. So one of those example data here. We have 4 rows, so there's only one example of fuzzy, so it gets 3. There's 2 examples of smooth, 4 and 5. So you just transform the G column into the mean within the group. So this is something that can work really well, and it kind of for obvious reasons. If you're trying to predict the target, the Y variable, then like directly encoding that is quite an intuitively nice thing to do. But it can run you into problems very quickly. as you can think of it, just like directly leaky, like, in one basic concept in machine learning is not letting your target leak somehow into your data set. This is a very direct example of that, since this is, the value in each row is directly used in the calculation of the group mean. So it'll create a feature that your model thinks is amazing and fits to very strongly, but is just useless when you go to unseen data. So this is kind of like this. I think this is not generally used in practice, but it's the simplest example, and there's a couple of variations on it that we'll move on to. I think one classic thing you see as when people are starting out machine learning is to calculate these means before splitting the data into training and holdout sets, which will just shoot yourself in the foot for doing any kind of valid measurement of the performance of your model. So instead of target encoding, what can we do? So leave one out is kind of a next step. So it's similar. So you're calculating group means, basically, but you leave each row itself out from the calculation. So again, tiny data set, it's a little bit trivial, but you have this in this row, value for fuzzy is 3, and for the leave one out value, you just do the average of the rest, all other examples of fuzzy. So in case there's 1, so it's just 4. For smooth, you can see that a little more variation. So the value of 6 is the average of 5, 6, 7, and similar for the others. So it's better. You're kind of not directly leaking the target into each observation, but in practice, especially with machine learning models that are quite flexible, you still end up overfitting. And there's 2 reasons here. One is that for each group, from a statistics point of view, if you're in your data set, you have a kind of a random sample of of each category, smooth. You might have a sample that's where the sample mean is above or below the true mean as a group, not just kind of individually. So, if in your data set you happen to have a group of smooth ones where it's just over, the sample mean is above the true kind of underlying mean for that group, then you're still going to tend to overfit. And I think more subtly, especially when you have complex models, it can actually kind of still figure out what the value is. Like if you notice for smooth, we have 4, 5, 6, 7, so increasing values, and then end up with decreasing values of the leave one out encoding. So like in general, the higher the value of the target for a particular row, the lower the value of the leave one out needs to be. So, it'll be a noisy signal for a machine learning model, but it can probably just pick out the reverse of it. And so this helps a bit compared to target encoding. It's certainly better than nothing, but in practice, you still find, I've never found that it can solve the overfitting problem. Here I have a link to an implementation of this. Oh, I have no internet. What am I doing here? I'm not on the Wi-Fi. So I'll try to get onto it, but we'll see. I'll just move on in the meantime. Okay, after leave one out, so I think what's more common is some kind of smooth target encoding. So basically the Z is your, the final variable that you come up with, and you have some weight between the group mean and the global mean. So the group mean is your in-group, so within smooth, for example, what's this mean versus the global mean, what's the mean of all of the y variables, and some weighting between those. And you generally set it up. It's not exactly this formula that's used in different cases, but it's this basic idea, and just generally W will go up for larger groups. So for a quite small group, maybe you'd have W is 10% and minus W is 90%, and so it's quite close to the global mean. And then as the size of the group increases, you put more and more weight on the group mean. And it's going to make intuitive sense because the smaller the sample, the noisier that sample is going to be, and the less you can trust that group mean. And let me just see if I've connected. Yes, okay, so there's a category encoders library. It's scikit contrib, so it's kind of related to but not part of scikit-learn. And there's a bunch, let's see if I can zoom in here. There's a bunch of kind of the things I'm talking about plus some others implemented as transformers that you can plug into scikit-learn pipelines. So there's a target encoder, before there's a leave one out encoder, and there's lots of others to look at if you're interested. I'm trying to hit the main ones now. One thing that I'm going to briefly mention, but not really talk about in detail, is embeddings. So if any of you are familiar with NLP, you'll be familiar with these. So word2vec was the kind of classic original version of this. So, well, maybe not the original version, but kind of the thing that repopularized it recently. Basically, the idea is you can map words to some like 100-dimensional, 500-dimensional vector space, and you can build it in a way that similar words are grouped together. So, I don't know, cat and bobcat and lion and would be close together and far away from something like truck or skyscraper. So, if you have the right data, this can be a very powerful approach. I'm not going to cover those in detail, so that this is more something to look into if it makes sense. I think the one thing I will say is that there are lots of pre-trained vectors available, so you can go out. There's a set of these. It's called GLOVE, which are very, very well known and totally public. And so if you have some data that's like keywords, and you want to kind of figure out which keywords are close to each other, you can just download a pre-trained set of these that were built on all of Wikipedia or something like that, and just stick them in. And there's been a couple models at QB where this has been just kind of off the shelf, really, really good approach without too much work. Okay, so those are all the basic encoding types. Next section, strategy. So this is meant like what kinds of things do you want to think about when you get a data set? You have categorical variables in it. What kind of things you should think about? First thing, always it's ever present, boring but very important. Cleaning it up. And so some of this is just wrangling stuff in pandas. As per usual, there's a few packages that I've used multiple times and have found helpful. So first is fuzzy wuzzy, which is basically fuzzy string similarity. So if you have two strings that are close but not exactly the same, you can get a score from 0 to 100. How similar are these? And so it's kind of useful if you're combining two sources or you want to group some things together. There's a few different ratios. RexPy is a little bit, I think, less known, and my mileage has varied with it, but there was at least one case where it was very helpful. So I want to do a little demo of it. I actually think I might have it up here. Okay, so this is RexPy. It's a Python package that you can install. This is a website which just has a live demo of it. And so I hope everyone can see this, but basically what we have here is kind of a set of, this is something that could be IDs. They all follow a similar pattern. But I think I want these numeric. But they're kind of, each of them are different. So RexPy will try to automatically discover regular expressions that capture that, and then you could use to match things against it. And so there's no correctness guarantees or even guarantees that we'll find a good solution, but I found it has worked fairly well. And what's helpful is that if you have something that's totally unrelated, so something that's very different, it'll return two separate results. And however, there's some there's things you can configure, but it'll basically sort out what's the minimal set of regexes that it'll take to describe this data. And so if you have different kinds of IDs or different things that are similar but different in a way that can be picked up by a regular expression, this might give you a really handy summary of what those are, and then you can use the regular expressions to create some aggregated groups of your data. That's been quite useful for me a couple different times. Dirty Cat is another Python package. There's a couple examples there, and one thing that I've kind of the most useful thing I've found is a similarity encoder, which is in a kind of similar, a word embedding kind of way. If you feed it a bunch of text, it'll try to group similar ones together and give them similarity scores. So, again, scikit-learn compliant, you can plug it into a pipeline, and you can get things like this. So this is an example straight from the Dirty Cat documentation, where we fed in some job titles, and this is kind of a multi-dimensional scaling of the resulting similarities that the encoder has come up with, and it's strings that are similar have been grouped together. And so this is done on just a pure, basically a string similarity kind of way. But if you do have data where there's kind of small variations, it might be a quick and easy way to group those into aggregate categories. So those things are all about cleaning the data set that you have. I'd say often found the most important thing to do is to think outside your data set a little bit. So there's some external data you can get that can explain how these groups are related. I think it's easy to get into a kind of Kaggle style mindset where you're okay, this is my data and I will build my model. But there's so much useful public external data out there that you often can almost certainly do better than that. So I just have kind of a few random examples off the top of my head. Geographic areas, there's a lot of obvious ones. If you have something like countries, the string of country name, your model's gonna have no idea which countries are beside each other. If you plug in latitude, longitude or something, you can get that. Maybe elevation is important, maybe population density is important, but it's kind of what relevant numbers can you find that will tell your model which of these categories are close to each other. For wine, you might look at, alcohol or sugar levels, something about what's in the wine, some online ratings scraped from a website. If you're working on a website and you have user sessions from different browsers, Firefox, Chrome, i.e. different versions of each, Maybe you just plug those in, or maybe there's something, maybe the release date of the browser will tell you something about the kind of user that you're interacting with. So I just think thinking about that kind of thing is quite important. Also, kind of similar to where we were looking at before, can you roll small groups up into larger ones? If you have, postcode data, maybe you need regions, or maybe you need countries, which will be kind of easier for your algorithm to deal with. And yes, so like I was saying before, if you have keyword type data, can you use some off-the-shelf embeddings? Maybe. So I think this is one side of my talk, but this is often, if you can get this right, sometimes changing things about your algorithm will give you 10% or 15% improvement, but finding a really good new external data source can be an order of magnitude difference. So it's definitely important to remember. What encoding should I use? If you have few, like if it's 4 or less, just definitely one hot encode it. And you can maybe scale that up as the data set size increases. And it kind of depends on how balanced your target is. If you have very imbalanced data, you're, say, at QB when we're predicting fraud, maybe 2% of claims have some sort of fraud associated with them. Your data set's effectively not as big as one with more balanced classes. But yeah, as it goes towards the smaller end, one encoding is a simple thing and it will work well. The more categories you go to, you want to, I think, lean more and more towards the target encoding approaches and some of the stuff that we're going to talk about with the gradient boosting libraries. Thing to think about is, do you care about interactions? So an interaction between something, an observation being in a certain group, and how it interacts with another variable. So, for example, I don't know, maybe thinking about browsers as the last example, maybe you have browsers, you're looking at conversion weights on your website. Maybe Firefox and Chrome have about the same average conversion, but they have a very different interaction with some other thing in your data set. If you target encode it and just get a new column, you're going to lose the information that those two groups are different. They're going to get the same or similar target encoding score, and your model's going to substantially lose its ability to figure out interactions. So if those are important, be cautious of that. And also just thinking about interpretability and maintainability. A nice thing about one hot encoding is it's very interpretable. You have a different column for each one. If you do something like count encoding, it's going to be a lot harder to explain to other people how it's working or show the precise effect of something being in this category. So I think those are the big things I would think about making these decisions. So feature importance for categories. I think this is a particular, like all scikit-learn estimators and other packages will have their kind of inbuilt feature importance. I'll tell you about your model. These are often quite inconsistent and sometimes misleading for categorical variables, especially tree-based models, where sometimes the feature importance is based on like how frequently it shows up in the trees, and you've one hot encoded something, it's going to not be very useful. So something that's totally model agnostic, like permutation importance. And there's implementation of this in the Explain Like I'm 5 package. And for those of you who don't know, permutation importance, basically you take your data set and your fitted model, and you use your holdout data set for this. So you can run it through the model, look at the predictions, calculate whatever your score is, R squared, log loss, whatever you're looking at. And then one column at a time, you shuffle the data in that column, make your predictions again, and check how much worse your score has gotten. If your score has gotten a lot worse, it's that variable is quite important in your for your model. And doing that on the holdout set can give you a really clear idea of like how, what features count for actual performance on unseen data. And so you can get, beyond what just the model has overfit on something and thinks this feature is amazing when it's not. So I think that's very valuable. If you want to know something about the different effects of different groups, SHAP values are a good approach. Let's go too far into them. There's quite a good package, and it's actually integrated into all of the top gradient boosting libraries. So it's actually quite easy to use. You could do a whole session about it, and I won't, but it's worth a look if you haven't heard of it before. Final section. So strategy. This will be specifically about the big three gradient boosting packages. Yes. So what do they do? In one line, XGBoost. It's really similar to scikit-learn. You basically have to pre-process things and only feed in numeric data. So you use one of the strategies we've talked about before. LightGBM has category-aware splits during tree building, which I'll explain a little bit, and CatBoost uses target encoding, and it does it in a way that's really good and resistant to overfitting problems we talked about before. So it's kind of in general, specific to decision trees, why can one-hot encoding be bad? And kind of in a nutshell, you end up doing things like this, where you're building trees and you're splitting them, and you can only split one group at a time. You have a column for a 0, 1 column for group 0 and group 1 and group 2, and you can only split one of them off at a time. And so if you're going to make some splits on groups, it's going to require a huge amount of splits, levels in your trees, and that's just going to be hard to cope with when you're imposing any kind of constraints on your trees. The way you prevent trees from overfitting is you limit the length, or the depth, or the number of splits, or the number of different trees in the model. And so if you have a kind of very hungry categorical variable with 10,000 columns that's eating up all your splits, it's going to be hard to find some parameters that work well for the category and for the regular numeric variables you have in the data set. So that's kind of the main problem. So LightGBM is category-aware splits, which basically means it can, if you have 10 groups, you can do a split with 5 and 5. Before splitting, you order group based on the target. This reference here, there's a cat smooth parameter and a max cat to 1 hot. So below a certain value, we'll just use 1 hot encoding, and then so smooth things. So basically, I've got a 1 minute warning, so I'm gonna wrap it up as quick as I can. But basically, you take the groups, say you have 10 groups, LightGBM will order them from some gradient, some Hessian, basically big positive errors on the right to big negative errors on the left, and then it will look for a split between those. And what the smooth cat parameter will do is take small groups, so like 8 here, and shrink them towards the center, which will affect where the split's found. But you can directly, as opposed to 1 hot encoding, you can do splits like this. I had a simulated example, which I'm going to kind of skip through in the interest of time, showing how increasing the cat smooth parameter increased your goodness of fit. Final thing, CatBoost. So this does target encoding, and the way it does that is you randomly shuffle your data a few times, and then you calculate basically target encoded statistics. So in this case, it's the mean of the variable, but you do it in a running total kind of way. So starting at the beginning of your data set, you know nothing, and then the values in the fourth row will be based on all previous instances of that example, and so on. And so it kind of naturally adds a little bit of noise to the variable in a way that when the tree fits on it later, it's not going to overfit nearly as badly. And so this is just purely the mean. Kind of in practice, there's a bit of smoothing as well between the global mean. So the mean of all the y I have in this table is 3.8. And so we'll start from there, and then kind of as it through the data set, things will, more and more data will be involved in the calculation, and these things may diverge more and more from the group mean. And so that is quite resistant to overfitting. And I think especially when you have a lot of very high cardinality variables, it works quite well. So that would push me towards cap boost in those situations. Final thoughts, really quick. There's no approach that's always best. The easy but not always useful answer is just try everything and test it. Often don't have time to do that. So I hope there's a bit of intuition, a bit of roadmap for different things you can try and when you might want to try those. And otherwise, thanks very much. That's all for me. And I'm happy to take questions if we have time.
Yeah, I was just going to say, so we have about 3 minutes or a few minutes for questions. At the back, I'll just pass the mic around.
As word of warning, I'm a little bit deaf. I was born genetically, so please speak up as much as you can.
All of this approach is quite, for encoding, like inelegant. So, like one hot, you get lots of variables. But hasn't somebody tried to do it in the API itself? Say, I've got a categorical variable, it's an ordinal, cardinal, whatever the labeling is. So you don't have ugly one-hot encoding.
Yeah.
Something more elegant. Hasn't somebody tried that?
So I actually didn't quite get it, unfortunately.
Has somebody tried encoding all this in the model, saying that I've got a variable which is categorical, its properties called ordinal, cardinal, ordinal. Rather than having one hot where you expand the number of variables, you embed it into the definition of the variable. It's more embedded in the API. So I've got a variable. So you say the variable's properties are it's an ordinal function, cardinal function, whatever you like.
I think so for like GBM and cap boost and stuff, as part of the API, you declare things as categorical or not at fitting time. Every other scikit-learn estimator is totally unaware of what it just numbers to it, so you have to figure it out before you feed it in.
Oh,
yes.
Some people use, for example, they would use LightGBM as they're training the model, and they would use XGBoost as the final iteration of the model. What about the categorical? Because the categorical feature functionality is different. So how would you, if you want to use XGBoost, what would you do about the categorical variables? Because XGBoost has less support.
So XGBoost, I think you have to think about it like you would scikit-learn, like everything. By the time your data hits XGBoost, it has to be a number. And it will just interpret it as numeric and split it, order it from low to high and split it. So I think if you're doing stacking, if you're trying different models and then using XGBoost as the final one, assuming that your earlier models, their outputs are numbers, then that'll be totally fine. If you're using XGBoost earlier on and you still have some strings in your data, you're gonna have to do something with them before putting them to XGBoost.
Great, last question, then I'll ask to take all the other ones offline, please.
Thanks very much. So the target encoding, I think, is fine. It's a lot like if you were to just fit a linear model straight away, and that would be your result, right? But when you do I'm wondering about the leave one out encoding when you're looking at the unseen data, because then you don't have a target to modify your mean value with.
Yeah, so the most is I think the leave one out implementation I mentioned will just, you'll kind of have two different processes for training data and test data. So the training data will have the leave one out adjustment applied, and then when you're fitting the encoder, it will also keep a list of all the true group means. And then when you're using it on unseen data, on your, if you're doing your validation or your models in production, it will use the full actual group mean. So leave one out adjustment is just done at training time. And I think intuitively what I think about it is just like it's making the variable a little less good, so that your machine learning model is not going to just jump on it and only fit on that and ignore all the other data in your data set.
Bit like regularization.
Bit like what?
Bit regularization.
Yeah. And it's kind of one thing people did before cat boost. So cat boost has that way of kind of making the variable worse by doing the kind of running total thing I explained. Well, something people used to do is they would target encode and then just add noise to it, so that when you're fitting your model, it doesn't look that powerful. And so doing some target encoding and then just adding some noise to it, as a just kind of very hacky way of regularization, actually sometimes works. So I think cat boost way is better, but that's kind of intuitively what people used to do before that was available.
All right, thanks very much. Yeah, we'll end it there, I suppose. And thanks very much, Liam. It was a great talk. And
Thanks, guys. Enjoy lunch.